Right now, at this very moment, the space between you and the screen you're reading this on is trying to tear itself apart. Every second, the universe manufactures thousands of miles of brand new space from absolutely nothing. And here's what will shatter everything you thought you understood about reality. It's not expanding into anything. No container, no cosmic warehouse, no outside. What you're about to discover will change how you see existence itself. We're going to trace the most disturbing journey in all of science, from the accidental discovery that broke physics, through invisible forces tearing reality apart, to a future so strange that astronomers living billions of years from now won't even know the universe had a beginning. Think you understand space? You're about to find out you've been living inside the greatest illusion ever created by nature itself. Let's begin. Picture yourself blowing up a balloon in your living room. The rubber stretches outward, pushing against the air. The balloon needs room to grow, and your living room provides that space. This is how every expansion works in your daily life. Plants grow into air, cities spread into countryside, ice expands across water. Always there's a container, always there's something to expand into. Your brain evolved to understand this kind of expansion. It's wired into your neural architecture after millions of years of evolution, in a world where everything that grows needs space to grow into. So when scientists tell you the universe is expanding, your brain does what it always does. It pictures that balloon. You imagine space stretching outward into something, some cosmic room, some vast emptiness waiting to be filled. There must be a boundary where our universe ends and something else begins. This feels so natural, so obvious, that even questioning it seems absurd. But here's where physics walks up to your comfortable assumptions and sets them on fire. The universe isn't like that balloon at all. When space expands, it doesn't push into anything. There is no cosmic living room. There is no container. There is no outside. The universe creates the very concept of space as it grows. Think about this for a moment. Really think about it. The universe isn't expanding into pre-existing emptiness. It's manufacturing the emptiness itself, creating the stage and performing on it simultaneously. Imagine trying to draw a circle bigger than your piece of paper, but instead of getting a larger sheet, the paper itself grows to accommodate your circle. In our world, this sounds impossible because everything we've ever observed expands into something else. But what if you are the paper and the drawing at the same time? What if there is no outside the paper to expand into? This isn't philosophy, this isn't a thought experiment. This is measurable, observable, documented reality, happening right now at scales so vast they make galaxies look like dust motes. Scientists discovered this mind-breaking truth by doing something deceptively simple: watching distant galaxies. In the 1920s, an astronomer named Edwin Hubble noticed something impossible. Every galaxy he could measure was racing away from us. Not just moving, fleeing, as if the entire universe were trying to escape from Earth. At first, this seemed to suggest we were at the centre of some cosmic explosion, like we were sitting in the middle while everything else flew outward into empty space, painting Earth as the special centre of creation. The reality turned out to be far, far stranger. Space itself is stretching. The galaxies aren't moving through space like cars on a highway. The space between them is growing, manufacturing new distance from nothing, carrying galaxies along like raisins in rising bread dough. The raisins don't move through the dough expands and carries them apart. Here's the part that breaks most people's minds. Imagine dots on a balloon surface, but run the deflation process in reverse. As the balloon inflates, the dots get farther apart without actually moving on the surface. The surface itself expands. Each dot sees every other dot moving away. No dot is special, no dot is at the centre. Now replace that two-dimensional balloon surface with the three dimensions of space you live in. The universe isn't expanding into anything because there is no anything for it to expand into. It's creating the very stage upon which expansion can happen. Every cubic inch of new space that pops into existence creates the concept of room to expand as it appears. This breaks our intuition so completely that even Albert Einstein initially rejected it. The man who revolutionized our understanding of space and time couldn't accept that space itself could grow. His equations predicted it, but he added a mathematical term specifically to prevent it, calling it his cosmological constant, a force that would keep the universe static and eternal. Later, when observations proved expansion was real, Einstein called this his greatest blunder. But we're getting ahead of ourselves, because before we can understand what the universe is doing, we need to understand how scientists even discovered this impossible process was happening in the first place. The answer lies in watching light itself get tortured by expanding space. When a distant galaxy fires a beam of light toward Earth, that photon begins its journey with a specific wavelength: blue light, red light, infrared. Each wavelength carries a signature, a cosmic fingerprint that identifies it as clearly as your DNA identifies you. But as the light travels through expanding space, something extraordinary happens. Something that provides the most direct evidence we have that space itself is growing. The space the light moves through gets larger during its journey. Imagine you're an ant walking across a moving walkway at an airport, but this walkway is slowly stretching as you walk. Your steps stay the same size, but the ground beneath you keeps growing longer. By the time you reach the end, you've travelled much farther than your steps should have taken you. Light experiences something similar, but instead of travelling farther, its wavelength gets stretched. Think about it like this. A photon of a light is a wave, rippling through space. If space itself expands while that wave is travelling, the wave gets pulled longer. It's like drawing a wave on a rubber band, then stretching the rubber band. The wave pattern elongates with the material. Blue light from a distant galaxy arrives at our telescopes as red light. Not because the galaxy moved away like a speeding ambulance changing its siren pitch. That's called Doppler shift, and it's different. The light gets redder because space itself expanded during the light's billion-year journey. Each wave of light gets pulled longer as the cosmic fabric grows beneath it. Scientists call this process cosmological redshift, and it proves beyond any doubt that space grows independent of the objects within it. Now here's the number that should rewire your brain. Light from the most distant observable galaxies has been stretched to nearly 40 times its original wavelength. Let that sink in. The space that light travelled through expanded so dramatically that what started as intense ultraviolet radiation, the kind that gives you sunburns, now reaches us as faint infrared heat. 40 times longer wavelengths means the universe expanded by a factor of 40 during that light's journey. Think about what this means. The galaxy that sent this ancient light looks tiny and faint in our most powerful telescopes. But when that light first left the galaxy billions of years ago, the universe was 40 times smaller than it is today. That galaxy was much, much closer to where our Milky Way would eventually form. Space didn't just grow a little bit, it underwent massive, relentless expansion. But here's what makes this even more disturbing. This stretching isn't happening somewhere else, far away in deep space. It's happening everywhere, right now. The space in the room where you're sitting is trying to expand. The space between your eyes and this screen wants to grow larger. You don't notice this expansion for one simple reason. Electromagnetic forces between atoms are far, far stronger than the expansion rate. The atoms in your body are held together by forces that completely overpower cosmic expansion at small scales. It's like trying to stretch a steel cable with your bare hands. The expansion of space is pulling on everything, but molecular and atomic forces are strong enough to resist it completely at the scale of your body, your planet, even your galaxy. Only across vast cosmic distances, millions and billions of light years, does this expansion become noticeable. The space between galaxies has no atomic forces to hold it together, so it expands freely, carrying those galaxies along for the ride. This is why the question, what is the universe expanding into, breaks down so completely. You're asking what the dough is expanding into, but you are part of the dough. You're asking what water is wet into. You're asking what exists outside of existence. The question assumes there's a beyond to measure against, but space itself defines what beyond means. However, if space is stretching everywhere, how far can we actually see? What limits our view of this expanding cosmos? The answer is more disturbing than you might imagine. You're trapped right now inside an invisible sphere, and you will never ever escape. Every night when you step outside and look up at the stars, you feel like you're seeing the universe, the whole thing, all of reality stretched out above you in that dark sky. But here's the truth that will reshape how you think about your place in existence. You're seeing less than 4% of what's actually out there. You live inside the ultimate cosmic prison, and the walls are made of something you can't break through, can't tunnel under, can't fly over. The walls are made of time itself. This prison has a radius of about 46 billion light-years. Beyond this boundary lies more universe, billions more galaxies, trillions more stars. Perhaps even other versions of you, living slightly different lives, reading slightly different versions of these words on slightly different planets. But you will never see any of it. Not with any telescope humanity could ever build. Not with any technology that could ever exist. The trap isn't made of walls or barriers. It's made of the finite speed of light combined with the finite age of the universe, stirred together with the relentless expansion of space. Light takes time to travel. When you look at the sun, you see it as it was 8 minutes ago, because that's how long light takes to cross the 150 million kilometers between the sun and Earth. When you look at the nearest star system, Alpha Centauri, you see it as it was over 4 years ago. Look at the Andromeda Galaxy, and you're seeing 2.5 million years into the past. The farther you look into space, the deeper you peer into history. Your telescope isn't just a device for seeing distant places, it's a time machine that only goes backward. Here's where the trap closes around you. The universe is 13.8 billion years old. This means the oldest light that could possibly reach you has been travelling for 13.8 billion years. Any galaxy farther than that might as well not exist from your perspective. Its light simply hasn't had enough time to reach you yet. But wait, the trap gets even more confining. Remember that space has been expanding this entire time. That distant galaxy was much, much closer to us when it emitted the light we see today. By the time its ancient light reaches our telescopes, expansion has carried that galaxy far beyond the simple 13.8 billion light-year mark. Run the calculations, account for expansion, and you get that number, 46 billion light-years. Today, right now, that galaxy whose ancient light is just reaching us sits roughly 46 billion light-years away from Earth. This creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists call the unobservable universe. You cannot see it, you cannot detect it, you cannot prove it exists. Yet logic and mathematics tell us it must be there. Think of yourself standing in a dense fog that limits your vision to 100 meters in any direction. You can see a circle of ground around you, but you know the world continues beyond that fog. You know there are mountains and oceans and cities beyond your limited view. You just can't see them. The observable universe is your fog-limited circle, while the actual universe stretches infinitely in all directions beyond your sight. If you're one of those people who likes to think about big numbers, here's one that should terrify and amaze you in equal measure. If the universe is infinite, and we have good reason to think it is, then your observable bubble contains exactly 0% of what actually exists. 0%. You can see 46 billion light-years in every direction, encompassing roughly 2 trillion galaxies, and you're seeing literally none of what's out there. It's like being an ant on an infinite beach, able to see only the few grains of sand immediately around you, while an endless desert stretches beyond your vision in all directions forever. But what lies beyond our cosmic prison walls? What exists in that unobservable realm? The answer is probably the most unsettling possibility in all of cosmology. More of the same. This sounds boring, but it's actually deeply disturbing. If you could somehow teleport 47 billion light-years away, beyond your observable boundary, beyond the cosmic horizon, you'd find yourself in a region that looks remarkably similar to here. More galaxies, more stars, more planets, possibly more life, possibly more intelligent civilizations wondering the same questions you're wondering right now. The universe appears to be homogeneous on the largest scales. Homogeneous means uniform, the same everywhere, like perfectly mixed cake batter, where every spoonful contains the same ingredients in the same proportions. Our observations of the cosmic microwave background, the ancient light from the early universe, suggest that space has this property. The tiny temperature variations we detect are smooth and consistent across the entire sky we can see. This smoothness tells us something profound about what lies beyond our sight. If the observable universe contains roughly 2 trillion galaxies, then a region of identical size just beyond our horizon should contain roughly 2 trillion galaxies as well, and another region beyond that, and another beyond that. The pattern continues forever, or at least much, much farther than we can comprehend. But here's where this gets psychologically disturbing. where your sense of uniqueness starts to break down. If space is truly infinite and homogeneous, then every possible arrangement of matter within any given volume must repeat somewhere. This isn't mysticism, this isn't philosophy, this is mathematical necessity. With infinite space and finite ways to arrange a finite number of particles, repetition becomes inevitable. It's not a question of if, it's a question of where. Imagine you have a deck of 52 cards. If you shuffle that deck infinitely many times, you must eventually get the same arrangement twice, 3 times, 1 billion times. Infinity guarantees repetition. The universe works the same way, but with atoms instead of cards. This means, and I need you to really absorb this, there are other versions of you reading these words right now. Not metaphorically, literally. In regions of space so distant that their light will never reach us, quantum mechanics has arranged matter in every possible way, including ways identical to your current configuration. There are versions of you where you decided to stop reading this sentence, versions where you were never born, versions where Earth never formed, versions where dinosaurs still rule, versions where humans evolved slightly differently, and you have blue skin or 3 arms or can breathe underwater. The mathematics suggests these copies exist at distances of roughly 10 to the 10 near 115 meters away. That's a number so large that if you tried to write it out, the line of digits would stretch across more space than exists in our entire observable universe. You'd need more atoms than exist in all the galaxies we can see just to write down this number in physical form. Yet if space is infinite, these distances are still finite, still real, still out there. Somewhere in the unobservable universe, another you is having this same realization about yet another you even farther away. And beyond that, another you is contemplating another you. The chain extends infinitely in all directions. Every decision you didn't make gets made by some version of you. Every word you didn't say gets spoken by another you. Every dream you abandoned gets fulfilled by a you in another cosmic horizon. But wait, this entire disturbing scenario assumes the universe beyond our horizon looks like the universe within it. What if it doesn't? Recent observations hint that our local region might actually be unusual. We seem to exist in what cosmologists call a cosmic void, a region with slightly lower than average galaxy density. If this is true, then travelling beyond our observable horizon might reveal denser regions of space, packed with more galaxies, more black holes, more stellar activity, or it might reveal regions that are nearly empty, vast stretches of space with almost no matter, just the occasional lonely galaxy floating in overwhelming darkness. Some theoretical models suggest that cosmic inflation, that rapid expansion in the universe's first fraction of a second, could have created regions with vastly different properties, different physical constants, different particle types, different laws of physics entirely. These pocket universes might exist just beyond what we can observe, operating under rules that would make our physics textbooks worthless, where gravity might be stronger or weaker, where light might travel at different speeds, where time itself might flow differently. We have no way to know. The observable universe is all we can ever interact with. Everything beyond is speculation, mathematics, and faith that the patterns we see here continue out there. But even these disturbing thoughts about what lies beyond assume something fundamental, that the universe is infinite. What if it's not? What if space has an edge? And if space has an edge, what lies beyond that edge? An infinite universe that expands presents one of the most beautiful paradoxes in physics, and understanding it requires breaking your brain in a very specific way. How do you make infinity bigger? Think about it. Mathematically, it should be impossible. Infinity plus anything still equals infinity. Infinity times 2 still equals infinity. You cannot add to something that already contains everything. Yet our observations clearly show that space is expanding everywhere. Even if the universe extends infinitely in all directions, distances between galaxies are growing. The fabric of space itself is stretching. So what gives? The solution comes from understanding what expansion really means. When cosmologists say the universe expands, they don't mean it grows larger in the sense of becoming more infinite. That's nonsense. They mean the scale of space itself increases. Think of it like this. Imagine an infinite piece of graph paper where each square is 1 centimeter wide. Now imagine stretching that paper so each square becomes 2 centimeters wide. The paper is still infinite. It still has infinitely many squares. But the distance between any two marked points has doubled. This is exactly what happens during cosmic expansion. The universe doesn't become more infinite. That's mathematically meaningless. Instead, the scale factor of space increases, making all distances grow proportionally. A galaxy that's 100 million light-years away today was only 50 million light-years away when the universe was half its current age. But both measurements are taken from an infinite universe. If you're thinking, wait, but how can something that's already infinite have been smaller in the past? Good. You're wrestling with one of the deepest mysteries in cosmology. Here's the disturbing implication. If the universe is infinite now, it was also infinite at the moment of the Big Bang. Let that sink in. The Big Bang wasn't an explosion of matter and energy from a single point into empty space. It was the simultaneous expansion of infinite, space filled with infinite energy at every location. Wrap your mind around this. The Big Bang happened everywhere at once across infinite space. There was no center, no edge, no outside. Just infinite space suddenly beginning to expand and cool. Every point in the universe can claim to be the center of expansion, because expansion looks exactly the same from every location. You're at the center. A galaxy 10 billion light-years away is at the center. An astronomer on a planet in the unobservable universe is also at the center. Everyone is at the center because there is no center. This infinite perspective solves several cosmic mysteries while creating new ones. It explains why the universe looks the same in all directions from our vantage point. In an infinite homogeneous space, every location is equivalent. It also explains why we don't see evidence of an edge or a center. There is no edge or center to see. But it raises a haunting question. If the universe contains infinite matter and energy, how do we avoid infinite density? The answer lies in recognizing that density is matter divided by volume. Even if both matter and volume are infinite, their ratio can still be finite. Like how infinity divided by infinity isn't necessarily infinity. It can be any number, depending on how you approach the limit. The universe can contain infinite stuff spread across infinite space, while maintaining a specific average density of about 5 hydrogen atoms per cubic meter. Here's where the paradox becomes personal. In an infinite universe, every possible event that can happen will happen infinitely many times. Not just those copies of you we discussed earlier. Every possible version of every possible story plays out somewhere in the vast expanse. Every tragedy, every triumph, every moment of beauty, every act of cruelty, everything that can happen does happen, and happens again and again, infinitely. If this troubles you, and it should, consider the alternative. A finite universe raises equally disturbing questions. What lies beyond its boundary? How can space itself have an edge? What happens if you try to travel past that edge? Do you hit a wall? Does space just stop? What does it even mean for space to stop? These questions led many scientists to prefer infinite models despite their conceptual difficulties. The simplest interpretation of our observations is that space extends infinitely in all directions. Recent measurements of the cosmic microwave background suggest our universe is either infinite or so absurdly large that any curvature is undetectable with current technology. The data points toward flat, infinite space. This means the expansion you observe isn't creating new space in the sense of adding rooms to a house. It's stretching the infinite fabric that already exists. But if space isn't being created, what exactly drives this relentless stretching? What force could possibly push infinite space apart? The answer involves one of the greatest discoveries in modern science and one of the deepest mysteries. The universe manufactures new space from pure nothingness at a rate that would make every factory on Earth weep with envy. Every single second, the volume of space within our observable universe increases by roughly 10^78 cubic meters. Let me help you understand how large that number is. If you tried to count to 10^78, saying one number per second, you'd need more time than the universe has existed, multiplied by itself billions of times over. You could start counting at the Big Bang, count through the formation of stars and galaxies and planets and life itself, count through the eventual death of everything, and you wouldn't even be close. That's how much new space comes into existence every second. All this space emerges from what physicists call the quantum vacuum. And here's the first thing you need to know about quantum vacuum. It's not empty. When you think vacuum, you probably picture perfect nothingness, the absence of everything. But quantum mechanics laughs at this idea. At the quantum level, what we call empty space is actually a seething foam of virtual particles popping into existence and annihilating each other in timeframes shorter than the smallest measurable instant. This process, called quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum achievable in a laboratory, this quantum activity continues, bubbling away beneath the surface of reality like water at a rolling boil. Think of space like the surface of the ocean. From an airplane, the ocean looks smooth and calm, but zoom in close and you see waves, ripples, foam, constant activity. Space is similar. From our macroscopic perspective, it looks empty and static, but at the smallest scales it seethes with quantum activity. Here's the mind-bending part. This vacuum energy has gravitational effects, but unlike matter, which pulls things together through gravity, vacuum energy creates repulsive gravity. It pushes space apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room there is for new vacuum energy. Do you see the problem? This creates a runaway feedback loop. During the universe's first tiny fraction of a second, this process ran absolutely wild. Space expanded faster than light could travel, not because anything moved faster than light, but because space itself grew faster than light could cross it. Imagine trying to walk across a treadmill that accelerates faster than you can run. You're moving forward at your top speed, but the ground beneath you is expanding backward even faster. You never reach your destination because the destination keeps receding. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to roughly the size of a basketball. This sounds like science fiction. It sounds impossible. But quantum mechanics doesn't just allow it. Quantum mechanics demands it. The uncertainty principle, discovered by Werner Heisenberg, tells us that energy can be borrowed from the vacuum, as long as it's paid back quickly enough. The more energy you borrow, the faster you have to pay it back. But during cosmic inflation, the universe found a loophole. It borrowed massive amounts of energy to create new space, then used the expansion itself to pay back the debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan and make a profit. The process works so perfectly that it overshot by an absurd margin. Inflation should have stopped after creating enough space to solve certain cosmological problems. Instead, it kept going, creating far, far more space than necessary. Our entire observable universe, every galaxy we can see, every star in the sky, represents just one tiny patch of the vastly larger inflated region. Think of blowing up a balloon to the size of planet Earth, then examining a patch the size of a pinhead under a microscope. That pinhead is our observable universe compared to the region inflation created. But here's what makes this truly bizarre. The process continues today, just at a much slower rate. Current expansion isn't inflation. That ended long ago. But expansion operates on similar principles, something called dark energy, which makes up roughly 68% of everything in the universe, behaves exactly like vacuum energy. It fills space uniformly. It creates repulsive gravity that accelerates expansion. And as the universe grows, more dark energy appears to fill the new space. This seems to violate every intuition you have about conservation of energy. Energy cannot be created or destroyed. That's one of the most fundamental laws of physics. Yet expansion seems to create new dark energy continuously, pulling it from nowhere, manufacturing cosmic fuel from the void itself. The resolution lies in understanding that gravitational potential energy is negative. As space expands, matter becomes more spread out, reducing the gravitational binding energy between objects. This negative energy balances the positive energy of newly created dark energy. The universe maintains perfect energy balance while creating infinite new space. It's the ultimate free lunch. Everything comes from nothing, and the books still balance. This process will continue forever, or at least for timescales longer than human minds can truly comprehend. Each moment brings new space, new dark energy, and accelerated expansion. The universe grows not because it needs room to expand into, but because expansion creates its own room. Yet all this cosmic creativity, this mind-bending ability to manufacture space from quantum foam, pales in comparison to what happened in that first fraction of a second after the Big Bang. What evidence do we have that this impossible-sounding story actually happened? How can we possibly know what occurred in the first trillionth of a second of cosmic history? The answer is hidden in static, literal static, the kind you used to see on old television sets between channels. In 1964, two radio astronomers at Bell Labs in New Jersey were having a very frustrating day. Arno Penzias and Robert Wilson were trying to eliminate annoying background noise from their horn-shaped antenna. No matter what they did, a persistent hiss remained in their data. They cleaned bird droppings off the equipment. New York pigeons had nested inside, and Penzias and Wilson thought maybe the, shall we say, organic deposits were causing interference. They recalibrated their instruments multiple times. They pointed the antenna in different directions across the sky. They checked for interference from nearby New York City. The noise never went away. It came from everywhere, equally, at all times. A steady hiss that permeated every measurement they made. What Penzias and Wilson had accidentally discovered, while scrubbing pigeon poop off a radio antenna, was the echo of creation itself. That noise was the cosmic microwave background, the afterglow of the Big Bang stretched and cooled by 13.8 billion years of expansion. This discovery earned them the Nobel Prize and provided the most direct evidence we have that the universe began in a hot, dense state, and has been expanding ever since. Here's why this radiation is so phenomenally important. It carries the signature of cosmic expansion, literally imprinted in its wavelength. When this light first escaped the early universe, about 380,000 years after the Big Bang, it was brilliant visible light with a temperature of about 3,000 degrees Celsius, hot enough to vaporize you instantly, hot enough to glow orange-white like molten metal. But as space expanded over billions of years, the wavelength stretched along with it. What started as intense visible photons became infrared radiation, then microwave radiation, then finally radio waves. Today, this ancient light reaches us at a temperature of just 2.7 degrees above absolute zero, one of the coldest things in the universe. Space has stretched these photons so much that they've lost almost all their energy. The cosmic microwave background is almost perfectly uniform, smoothed to within a few parts in 100,000. This uniformity proves the early universe was incredibly homogeneous, just as inflation theory predicts. Without inflation's rapid expansion to smooth out irregularities, we should see dramatic temperature variations across the sky. Different regions of the early universe should have had wildly different properties. Instead, we see near-perfect uniformity. It's like perfectly mixed cake batter. Every sample you take has the same ingredients in the same proportions. But those tiny temperature variations that do exist, those few parts in 100,000, tell an even more remarkable story. They represent quantum fluctuations that inflation stretched from subatomic scales to cosmic scales. Think about that. Random quantum jitters, the fundamental uncertainty built into reality at its smallest level, got amplified to galaxy-sized proportions. These microscopic ripples in the early universe eventually became the seeds that grew into galaxies, stars, planets, and you. You exist because of quantum uncertainty amplified by cosmic expansion. You are the descendant of random fluctuations in quantum fields during the first fraction of a second after the Big Bang. Advanced satellites, first the Cosmic Background Explorer, COBE, in 1989, then the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001, and finally the Planck satellite in 2009, have mapped these temperature variations with exquisite precision. The patterns they reveal match inflation theory predictions so precisely that cosmologists can measure fundamental properties of the universe from this ancient light. We can determine that space is geometrically flat to within measurement error. We can calculate that ordinary matter, the stuff you're made of, the stuff making up stars and planets, comprises only about 5% of the universe's total energy content. We can measure the expansion rate and age of the cosmos to remarkable accuracy, all from studying static, from analysing the hiss of creation itself stretched by expansion into a whisper. But the cosmic microwave background reveals something even more profound. The observable universe today, everything we can see, was once compressed into a region roughly the size of a beach ball. Every galaxy visible to our most powerful telescopes, every star in the night sky, every planet, every black hole. All of it once occupied a volume smaller than what you could hold in your arms. This compression wasn't like stuffing matter into a small container. Space itself was compressed. The beach ball didn't contain the early universe. The beach ball was the early universe. There was no outside, no surrounding space, just that compressed region of space-time beginning its expansion into the cosmos we inhabit today. Let me give you some sense of scale here. If you could somehow compress all the matter in the observable universe, roughly 1053 kilograms of stuff, back into that early state, the density would be about 1094 grams per cubic centimetre. For comparison, the densest material on Earth, osmium, has a density of about 22 grams per cubic centimetre. The core of the Sun reaches maybe 150 grams per cubic centimetre. A neutron star, one of the densest objects we know of, has a density around 10^2 grams per cubic centimetre. The early universe was 1080 times denser than a neutron star. Numbers this large stop having meaning to human intuition. We can write them down, calculate with them, but we cannot truly comprehend them. This realization leads to a disturbing question. If all the space we can observe was once compressed into such a tiny volume, what was providing the energy to drive such dramatic expansion? The answer involves a force that makes up more than 2/3 of everything, yet remains completely invisible. How do you detect something that hides in plain sight? In 1998, two teams of scientists set out to measure how much the universe's expansion was slowing down. Instead, they discovered that expansion is speeding up. This discovery won the Nobel Prize in Physics. It also shattered our understanding of cosmic evolution and revealed that we don't understand what 68% of the universe is made of. For decades, astronomers had assumed that gravity would eventually win its battle against expansion. All that matter in the universe, galaxies, stars, planets, gas, dust, should act like a cosmic brake, gradually slowing expansion until everything either stops growing apart or begins collapsing back together in a big crunch. Both teams were studying Type Ia supernovae, exploding white dwarf stars that detonate with nearly identical brightness. These stellar explosions make perfect standard candles for measuring cosmic distances, like lighthouses with known wattage that you can use to calculate how far away they are. When they plotted distances against redshift measurements, how much space has expanded during the light's journey, they found something impossible. Distant supernovae were fainter than expected. This meant they were farther away than the standard expansion model predicted. Somehow, space had grown more than it should have during the light's journey to Earth. The only explanation, expansion itself, was accelerating. Something was pushing space apart with increasing strength, overpowering gravity's pull, driving galaxies farther apart at faster and faster rates. Scientists call this mysterious force dark energy, and it dominates everything. Dark energy makes up roughly 68% of the total mass energy content of the universe. It outweighs all ordinary matter, every atom in every star, planet, and living thing, by more than 13-1. It even outweighs dark matter, the invisible scaffolding that holds galaxies together, yet we have absolutely no idea what it is. Here's what makes dark energy so profoundly weird. It doesn't clump or dilute. Normal matter becomes less dense as space expands. Spread a fixed amount of matter across twice as much space, and you get half the density. Simple conservation. But dark energy maintains constant density even as space grows. As the universe expands, new dark energy appears to fill the additional volume, like a gas that refuses to thin out no matter how much you expand its container. This means dark energy's total influence grows over time. In the early universe, when everything was compressed together, matter and radiation dominated cosmic evolution. Dark energy existed, but its effects were negligible compared to the gravitational pull of all that concentrated matter. As expansion spread matter thinner and thinner, dark energy's repulsive influence became more apparent. About 5 billion years ago, roughly when our solar system formed, dark energy became the dominant force in cosmic evolution. Before that moment, expansion was slowing due to gravitational attraction between galaxies. After that moment, expansion began accelerating due to dark energy's repulsive push. We live in the age of acceleration. Every day, dark energy becomes more influential. Every day, expansion accelerates a bit more. This acceleration is subtle over human timescales. You won't notice it in your lifetime, or in 1,000 lifetimes, but over cosmic timescales, it's dramatic. In the far future, dark energy will dominate so completely that distant galaxies will accelerate away from us faster than light can travel between them. They will disappear from our observable universe forever. Their light stretch to wavelengths longer than the universe is wide. But what exactly is this invisible force that controls the fate of everything? The leading candidate is vacuum energy, those quantum fluctuations we discussed earlier that fill every point in space. Quantum field theory predicts that empty space should contain enormous amounts of energy from virtual particles constantly appearing and disappearing. When physicists calculate how much energy the vacuum should have based on quantum mechanics, they get an answer that's 10 Cn 20 times larger than what we observe. Let me emphasize this. Our best theory for how quantum fields work predicts a vacuum energy density that's off by a factor of 10 by 120. That's 1 followed by 120 zeros. This represents the worst prediction in the entire history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels out 99% with 129s of the vacuum energy, leaving just enough to drive cosmic acceleration. Alternative theories suggest dark energy might be a new field pervading space, similar to the electromagnetic field but with different properties. Some physicists call this field quintessence and propose it might change strength over time, unlike the cosmological constant which remains forever fixed. Others propose modifications to gravity itself at cosmic scales. Perhaps Einstein's equations need correction when applied to distances of billions of light years. The truth is, we are as ignorant about dark energy as ancient humans were about the nature of lightning. We can measure its effects with precision. We can predict its influence on cosmic expansion, but we have no idea what it actually is. This ignorance matters because dark energy determines the fate of everything. If dark energy remains constant, the universe will expand forever, approaching heat death as matter spreads infinitely thin. If dark energy strengthens over time, expansion might accelerate so violently that it eventually tears apart galaxies, stars, planets, and even atoms themselves in a catastrophic big rip. If dark energy weakens or becomes negative, expansion might slow, stop, and reverse into a big crunch, collapsing everything back into a hot, dense state. Our cosmic destiny depends on understanding this invisible force, yet it remains one of the deepest mysteries in all of science. But dark energy's current influence, as mysterious as it is, pales in comparison to an even more dramatic period of expansion. During the first fraction of a second after the Big Bang, expansion accelerated so violently that it makes today's dark energy look gentle by comparison. What happens when expansion itself expands faster than the speed of light? During the first trillionth of a second after the Big Bang, the universe expanded more rapidly than it has in all the 13.8 billion years since. This period, called cosmic inflation, stretched space so violently that regions of the universe lost contact with each other forever. Points that were once close enough for light signals to travel between them were suddenly separated by distances that light could never cross. The universe broke its own speed limit. Nothing can move through space faster than light. That's Einstein's cosmic speed limit, and it's absolute. But space itself has no such restriction. During inflation, the distance between any 2 points doubled every tiny fraction of time, and this doubling happened so rapidly that light couldn't keep up with the growing separation. Think of it like a video game where you're running toward a goal, but the game developers are stretching the map faster than you can run. You're moving at maximum speed, but the distance to your objective keeps increasing. You're not moving slower. The space between you and your goal is growing faster than you can traverse it. Here's the number that will break your brain. Inflation increased the size of the universe by a factor of at least 10^26. Let me give you context for how absurdly large this is. That's like taking a grain of sand about 0.5 millimeter across and expanding it until it's larger than the entire observable universe today. Billions of light years across. From something you could barely see to something containing trillions of galaxies. This expansion happened in about 10^35 seconds. To put this timescale in perspective, light travels about 30 centimeters in 1 nanosecond, 1/1000th of a second. During inflation, the universe expanded by more than 26 orders of magnitude, in a time so incomprehensibly short that light could cross less than the width of a proton. If you tried to measure this time interval, you'd need a clock that ticks trillions of times faster than anything physically possible. The duration of inflation compared to 1 second is like 1 second compared to billions of times the current age of the universe. The energy driving this insane expansion came from what physicists call the inflaton field, a hypothetical quantum field that filled all of space in the early universe. Unlike other quantum fields, which have minimum energy states of 0, the inflaton field got stuck in a high energy state called a false vacuum. Think of it like a ball sitting in a bowl on a high shelf. The ball wants to roll down to the ground. That's the true minimum energy state, but it's trapped in the bowl, a temporary minimum that's not the lowest possible position. The ball's in a false vacuum, waiting for something to knock it out of the bowl so it can fall to its true ground state. While stuck in this false vacuum, the inflaton field created a temporary form of dark energy far more powerful than anything we observe today. This energy didn't dilute as space expanded. Remember, dark energy maintains constant density even as volume grows. So as the universe expanded, more vacuum energy appeared, driving even faster expansion. Exponential growth. The kind that sneaks up on you. If you fold a piece of paper in half 42 times, which is physically impossible, but bear with me, the thickness becomes equal to the distance from Earth to the Moon. Double it 7 more times, and you reach the Sun. The universe experienced something similar during inflation, but far more extreme. Every tiny instant during inflation, space doubled in size, then doubled again, then again. In the time it takes light to cross the width of a proton, space doubled dozens of times. This process solved several major problems in cosmology while creating fascinating new ones. First, it explains why the cosmic microwave background looks so uniform across the sky. Without inflation's rapid expansion to smooth out irregularities, different regions of the observable universe should show dramatically different temperatures. They were never in contact with each other, never had time to equilibrate to the same temperature. But if inflation happened, regions that are now separated by billions of light years were once close enough together to reach the same temperature before inflation stretched them apart. Inflation took a tiny, uniform patch of space and blew it up to cosmic scales. Second, inflation explains why space appears geometrically flat. Even if the universe started with significant curvature, bent like a sphere or saddle, inflation stretched that curvature so much that any remaining bend became undetectable. It's like inflating a balloon until its surface becomes the size of a planet. Stand on that surface, and it looks perfectly flat from your tiny perspective, even though the balloon still technically has curvature. But inflation's most profound consequence involves quantum mechanics, and this is where things get truly wild. During inflation, quantum fluctuations in the inflaton field were stretched from subatomic scales to cosmic scales. These microscopic variations in energy, density, random quantum jitters no larger than elementary particles, got amplified to sizes larger than galaxies. Think about that. The fundamental uncertainty built into reality at the quantum level got blown up to astronomical proportions. What started as quantum foam became the blueprint for cosmic structure. Every structure in the universe, every galaxy, every star, every planet, every atom in your body, traces back to random quantum events that happened during the universe's first moment. You exist because of quantum uncertainty amplified by inflation. Your galaxy formed from a quantum fluctuation. The solar system condensed from gas and dust that clumped together because of density variations created by quantum randomness during inflation. You are the descendant of quantum foam. But inflation raises a disturbing possibility, one that keeps cosmologists awake at night. If it happened once, it might happen again. The same quantum fields that drove primordial inflation might still exist throughout space, waiting for the right conditions to trigger another episode of exponential expansion. This could happen anywhere, anytime, even here, even now. A new bubble of inflation could nucleate in this room without warning, expanding outward at the speed of light, destroying everything in its path. Inside the bubble, different physics would apply. The strength of fundamental forces would change. Particles would have different masses. The laws of nature we depend on would cease to function. Our atoms would disintegrate. Chemistry would become impossible. Reality as we understand it would dissolve, and we would never see it coming. The bubble wall travels at light speed, so the first signal that it exists would be the moment it destroys you. No warning, no escape, just instant annihilation, as the physics that hold you together suddenly changes to physics that doesn't allow your existence. Yet this terrifying possibility pales compared to inflation's most mind-bending implication, one that suggests our universe might be just one bubble in an infinite sea of realities. Right now, while you read these words, trillions of other universes might be inflating into existence, each with different laws of physics, different constants of nature, different possibilities for life, consciousness and meaning. It isn't science fiction. This is the logical consequence of inflation theory. If inflation happened once in our cosmic history, quantum mechanics suggests it should happen continuously throughout a larger space called the multiverse. Random quantum fluctuations can trigger new episodes of inflation anywhere, at any time, constantly. Each episode creates a bubble universe that expands and cools, potentially developing its own galaxies, stars, planets, and maybe even life. Our universe would be just one bubble in an infinite foam of realities, floating in a vast sea of space-time we can never observe or interact with. Here's what makes this possibility so profoundly disturbing. Each bubble universe might have completely different physical laws. The strength of gravity could be different, maybe 1,000 times stronger, maybe 1,000,000,000 times weaker. The mass of electrons could vary. The speed of a light might not be constant. The number of spatial dimensions might not equal 3. Most of these universes would be uninhabitable wastelands where life as we understand it cannot exist. In some bubbles, gravity might be so strong that stars collapse immediately into black holes. No stable stellar burning, no light, no warmth, just gravitational collapse everywhere, all the time. In others, gravity might be so weak that matter never clumps together to form structures. No galaxies, no stars, no planets, just diffuse gas spreading thinner and thinner forever, never organizing into anything complex or interesting. Some universes might have no electromagnetic force, making chemistry impossible. Atoms couldn't bond, molecules couldn't form. Life as we know it, based on complex molecular interactions, couldn't exist. Others might exist in a state of eternal inflation, never cooling enough for particles to condense out of the quantum soup. These universes would remain forever trapped in their own creation event, expanding exponentially with no structures ever forming. The vast majority of bubble universes would be sterile, dead, boring. But in an infinite multiverse, even the most unlikely possibilities must occur somewhere. No matter how improbable our specific combination of physical constants might be, infinite bubbles means infinite opportunities for those constants to align perfectly for life. We exist in a habitable bubble not because we're special, but because we can only exist in habitable bubbles. This is called observer selection bias. We observe a universe suitable for observers because unsuitable universes don't produce observers to notice them. The multiverse doesn't care about you. It doesn't care about life. It churns out infinite bubble universes with random properties, and occasionally, by pure chance, one of those bubbles has the right conditions for complexity to emerge. This reasoning, called the anthropic principle, explains why our universe seems fine-tuned for life. We don't live in a universe designed for us. We live in the rare type of universe where observers like us can evolve to ask such questions. But the multiverse concept raises profound philosophical problems that cut to the heart of meaning and identity. If infinite universes exist, then every possible event happens somewhere. Every decision you didn't make gets made by another version of you in another bubble. Every tragedy you avoided befalls another version of you somewhere else. Every dream you never achieved comes true for another you in a different reality. The multiverse contains infinite copies of you, scattered across infinite realities, experiencing every possible variation of your life. This infinite replication makes the concept of uniqueness meaningless. You're not unique if infinite versions of you exist. Your choices don't matter if every possible choice gets made by some version of you. Your universe isn't special if infinite similar universes exist alongside it. Think about what this means for free will if every choice you could possibly make gets made by some version of you in some bubble universe. Did you really choose anything? Or are you just one thread in an infinite tapestry where every possible story plays out? Some versions of you reading this script right now will stop in the next sentence. Others will finish it. Others never started. Others live in worlds where this script was never written, because YouTube was never invented, because the internet was never developed, because computers work differently, because physics is different, because they're bubble nucleated with different initial conditions. Every variation exists. Every possibility is realized somewhere, yet the multiverse remains fundamentally unobservable. By definition, other bubble universes lie beyond our cosmic horizon. Their light can never reach us. Inflation stretched space so much that bubbles are separated by distances vastly larger than light can travel in the age of any universe. Their gravitational effects cannot influence us. Their particles cannot interact with ours. We can never prove they exist or determine their properties. The multiverse concept makes predictions that cannot be tested, and this troubles many scientists who argue that untestable theories don't qualify as science. Science requires falsifiability, the ability to prove something wrong through observation or experiment. If we can never observe other universes, never detect their influence, never test whether they exist, then is the multiverse really science? Or is it metaphysics dressed in mathematical clothing? But here's the counter-argument. The mathematics of inflation strongly suggests eternal inflation and continuous bubble nucleation. The same quantum field equations that explain our universe's early expansion predict ongoing expansion and bubble formation throughout the larger multiverse. If we accept inflation, and we have good observational evidence for it, we must accept its consequences, even if those consequences are unobservable. Recent observations have begun testing inflation's predictions more precisely. The cosmic microwave background contains subtle patterns, slight variations in temperature and polarization, that match inflation theory remarkably well. The Planck satellite measured these patterns with unprecedented accuracy, and they align almost perfectly with what inflation predicts. Every new observation strengthens confidence in inflation, while indirectly supporting the multiverse concept. We might be living in the best evidence for infinite other worlds, we just can't see them directly. Yet even this mind-bending possibility assumes our universe has only the three familiar dimensions of space we experience every day. Recent advances in theoretical physics suggest reality might be far stranger than even the multiverse implies. What if expansion happens in directions we cannot perceive? What if space has more dimensions than we can detect, and the universe is expanding into regions that don't exist for us? The universe might be expanding in directions that don't exist for you. String theory, our most ambitious attempt to unify all of physics into one coherent framework, requires space to have 9 dimensions instead of the 3 you experience. 6 additional dimensions of space exist right here, right now, all around you, but they're curled up so tightly that even particles cannot detect them. These hidden dimensions might be expanding along with the familiar ones, stretching in directions you cannot point to, cannot move in, cannot even conceive of properly. Imagine you're an ant walking on a garden hose. From your perspective, you can move forward or backward along the hose. You experience what seems like one-dimensional space. But the hose actually has 3 dimensions. The circular dimensions around the hose are so small compared to your size that you cannot perceive them. You walk along the hose completely unaware of the hidden dimensions curled up beneath your feet. We might be like that ant, aware of only 3 spatial dimensions while 6 others remain curled up beyond our perception, smaller than atoms, smaller than protons, possibly as small as the Planck length. 1035 meters, the smallest distance that has meaning in physics. If these extra dimensions exist, they could provide a literal answer to the question, what does the universe expand into? Our familiar 3-dimensional space might be expanding into the higher dimensional space that contains it, like a balloon surface expanding in 3-dimensional air. Our space might be a 3-dimensional membrane, physicists call it a brain, floating in 9-dimensional hyperspace. This concept, called the brain world model, suggests everything we can observe is confined to this 3-dimensional brain. Every particle we know about, every force except gravity, exists only on our brain and cannot escape into the extra dimensions. Gravity alone can leak into the extra dimensions, which explains why gravity is so much weaker than other fundamental forces. The electromagnetic force is 10 to the 36 times stronger than gravity, a truly absurd ratio. Maybe gravity seems weak because most of its strength escapes into dimensions we can't access. The expansion we observe might be our brain stretching within the larger hyperspace. As time passes, our three-dimensional membrane grows larger in ways we can measure, while also possibly shifting or vibrating in the extra dimensions in ways we cannot detect. But here's what makes this possibility truly mind-bending. Other brains might exist parallel to ours in the extra dimensions. These parallel universes could be separated from us by less than a millimeter in the fourth spatial dimension, a direction we cannot point to or move in. Another version of you might exist just a tiny distance away in a direction that doesn't exist in your three-dimensional space. You could be standing right next to a parallel universe and never know it, because next to doesn't mean anything when you're separated by extra dimensions. It's like two characters in different video games displayed on screen sitting side by side. The characters are inches apart in three-dimensional space, but infinitely far apart within their respective game worlds. They exist in separate realities that don't overlap, can't interact, can't even detect each other despite being physically adjacent. These parallel brains could occasionally collide in the higher dimensional space, and when they do, the collision releases enormous amounts of energy. The cosmic microwave background we detect might be the afterglow of our brain's collision with another brain in hyperspace. This collision would have provided the energy for inflation, jump-starting the expansion that created our observable universe. What we call the Big Bang might actually be a big splat, the moment our brain crashed into another brain floating through hyperspace. Every few trillion years, the brains might collide again, creating a new Big Bang and restarting cosmic evolution. The universe goes through cycles of expansion, collision, rebirth, expansion again. Our current expansion phase is just one beat in an eternal cosmic rhythm, but the mathematics of extra dimensions creates even stranger possibilities than cyclic collisions. Some models suggest the extra dimensions themselves might be expanding, while our familiar three dimensions remain relatively static. From our perspective, trapped in three dimensions, we would observe this as our space growing. In reality, the hidden dimensions might be doing all the expanding while our dimensions stay put. Think of a balloon where the surface area stays constant while the interior volume grows. We live on the surface, so we would never directly detect the interior expansion. We'd only see its indirect effects on the geometry of our three-dimensional space. Alternative models propose that some dimensions expand while others contract. The universe might be stretching in the directions we can see, while shrinking in directions we cannot. The total volume of space, accounting for all dimensions, could remain constant even though our three-dimensional slice appears to grow. These possibilities remain highly speculative because we cannot directly probe extra dimensions. The Large Hadron Collider, our most powerful particle accelerator, smashing protons together at 99.9999% the speed of light, can search for signs of extra dimensions by looking for particles that seem to disappear into hyperspace. When particles collide at high energies, if extra dimensions exist, some of the collision energy might escape into those dimensions, appearing as missing energy in our detectors. So far, no such evidence has been found. Either the extra dimensions don't exist or they're curled up even more tightly than theory predicts, requiring energies beyond what current technology can achieve to probe them. Yet the mathematics of string theory continues to suggest that extra dimensions are necessary for a complete description of reality. The equations only work, only remain consistent, if space has more than three dimensions. If extra dimensions exist, they fundamentally change what cosmic expansion means. The question, what does the universe expand into, might have a simple answer. It expands into dimensions you cannot see, cannot detect, cannot imagine, but which are as real as the three dimensions you experience every moment of your life. But even if extra dimensions don't exist, the shape of our familiar three-dimensional space might hold surprises that make the expansion question meaningless in unexpected ways. What if space curves back on itself? What if you could travel in a straight line and eventually return to your starting point? What if the universe is shaped like a donut? The universe might be shaped like a donut, and expansion might be nothing more than the donut getting fatter. This sounds absurd, comedic even, until you realize that the shape of space determines what expansion actually means. In a flat, infinite universe, expansion stretches space toward no particular destination. Distances grow, but there's no overall shape changing because space extends infinitely in all directions. But in a curved, finite universe, expansion might simply increase the size of a closed shape that wraps back on itself. The universe gets bigger, not by growing into something external, but by increasing its internal volume while maintaining the same topology. General relativity, Einstein's theory of gravity and space-time, allows three possible geometries for space, and each one creates a different picture of what expansion means. First, flat geometry. Space could be flat like an infinite sheet of paper. Parallel lines remain parallel forever. The angles of a triangle add up to exactly 180 degrees. This is Euclidean geometry, the kind you learned in school, extending infinitely in all directions. In flat space, expansion means distances growing proportionally. A galaxy 100 million light-years away today was 50 million light-years away, when the universe was half its current size. Simple, intuitive. Second, positive curvature. Space could be curved like the surface of a sphere. Parallel lines eventually meet. Triangle angles add up to more than 180 degrees. In this closed geometry, space is finite but has no edges, just like you can walk around Earth's surface forever without finding an edge or boundary. In positively curved space, you could travel in what feels like a straight line and eventually return to your starting point. The universe would have a finite volume, and expansion means this volume increasing over time. The sphere of space grows larger, but there's still no outside to expand into. The surface itself is all there is. Third, negative curvature. Space could be curved like a saddle. Parallel lines diverge. Triangle angles add up to less than 180 degrees. This open geometry stretches infinitely, but with curvature that makes distances behave strangely. In negatively curved space, expansion works similarly to flat space, infinite volume growing proportionally, but the geometry affects how light travels and how structures form. Current observations suggest our universe is either flat, or so incredibly close to flat that any curvature is undetectable with current technology. The cosmic microwave background data from the Planck satellite indicates the curvature parameter is less than 0.4% away from perfectly flat. But flat doesn't necessarily mean infinite. A sheet of paper is flat, but you can roll it into a cylinder, connect the edges, and you create a torus, a donut shape. The geometry remains locally flat, but the overall topology becomes finite and closed. Our universe could have this kind of structure. Space might be flat when you measure small regions, but wrapped around itself on cosmic scales, creating what mathematicians call a flat torus topology. If space wraps around itself like this, asking what it expands into becomes meaningless. A donut getting larger doesn't expand into anything external, it simply becomes a bigger donut. The volume increases, the surface area grows, but there's no outside space being filled. This wrapped geometry would create observable effects that astronomers have searched for. In a donut-shaped universe, light could travel around the entire universe and return to its starting point. You might see multiple images of the same distant galaxy in different directions in the sky. The same object viewed from different angles as light takes different paths around the cosmic donut. The cosmic microwave background might show repeating patterns where light has circled the universe multiple times, creating correlations between temperature fluctuations in opposite directions of the sky. Astronomers have searched intensively for these signatures. They've analysed the cosmic microwave background looking for repeated patterns. They've searched for matching galaxy formations in opposite directions. So far, they've found nothing. Either our universe is much, much larger than the observable region, so large that light hasn't had time to circle it even once in 13.8 billion years, or space doesn't wrap around itself at scales we can detect. The universe might be a donut, but a donut so enormous that our observable bubble represents just a tiny patch, far too small to detect the overall topology. But the shape question becomes even more complex when you realize that space and time form a unified four-dimensional fabric. The universe's shape includes not just the three dimensions of space, but also the dimension of time. Expansion doesn't just stretch space, it affects the relationship between space and time throughout the cosmos, warping the very flow of temporal experience itself. Time itself is stretching along with space, and this changes everything about how the universe ages. When Einstein revealed that space and time form a unified fabric called space-time, he showed us that you cannot stretch one without affecting the other. As cosmic expansion pulls space apart, it also stretches the flow of time throughout the universe. This isn't just theoretical physics, it's measurable reality with observable consequences. Imagine you're watching a distant galaxy through a telescope. That galaxy appears to be moving away from you due to expansion. But here's what breaks your intuition. Events in that galaxy appear to unfold in slow motion compared to events happening nearby. A supernova explosion that takes 3 weeks to brighten and fade in a nearby galaxy takes much longer when observed in a distant, rapidly receding galaxy. The explosion itself happens at the same rate in the galaxy's reference frame, but by the time the light reaches us, time dilation has stretched every moment. This time dilation happens because the light carrying information about those events gets stretched during its journey. Not just the wavelength of the light, but the time intervals between photons get extended. The universe literally stretches time itself. In regions of space that are expanding rapidly relative to us, time appears to crawl from our perspective. An hour there might correspond to days or weeks here, depending on how fast that region is receding. Here's the number that demonstrates this effect. Light from galaxies at the edge of our observable universe is redshifted by a factor of about 10. This means those galaxies were receding at roughly 90% the speed of light when they emitted that light. Events in those galaxies appear to unfold 10 times slower than events happening here. A supernova that takes a month to fade from our perspective took only 3 days from the perspective of that distant galaxy. This creates a bizarre situation where the age of the universe depends on your location, or more precisely, your state of motion through space. From our perspective here on Earth, the universe is 13.8 billion years old. But if you could somehow observe from one of those distant, rapidly receding galaxies, our region of space would appear younger. The relative motion would make it seem like less time has passed here. There's no absolute now that extends throughout the universe. Simultaneity, events happening at the same time, only makes sense locally. Different observers define now differently based on their motion through space. This temporal stretching reveals something profound about cosmic evolution. The early universe didn't just contain more compressed space, it contained more compressed time. Processes that take billions of years today happened much faster in the dense early cosmos. The formation of the first stars, the first galaxies, the first black holes, all occurred in a universe where time itself flowed differently than it does now. But expansion affects more than just the rate of time's passage. It changes the very concept of simultaneity across cosmic distances. In our everyday experience, simultaneity seems obvious. If two events happen at the same time, they happen at the same time everywhere. But relativity and cosmic expansion shatter this assumption completely. Events that appear simultaneous to you happen at different times according to observers in distant galaxies. There is no universal now that applies everywhere in the universe. The present moment is local, not universal. As expansion accelerates, these temporal effects become more dramatic. Dark energy's influence grows stronger over time, stretching space faster and faster, and stretching time along with it. This acceleration accelerates time dilation effects. Future civilizations in our galaxy will observe even more extreme time dilation when looking at distant galaxies. Eventually, expansion will stretch time so much that distant events appear completely frozen, as if time itself has stopped at the cosmic horizon. But this accelerating expansion raises a terrifying question about the ultimate fate of everything. What happens when expansion becomes so extreme that it overwhelms every force in nature? What happens when space stretches so violently that it tears apart galaxies, stars, planets, and eventually even atoms themselves? The universe is racing toward a state so cold and empty that no process capable of generating energy will remain possible, anywhere, ever. This inevitable destination, called heat death, represents the ultimate victory of cosmic expansion over every other force in nature. As space continues stretching forever, it will spread matter and energy so thin that the universe becomes a lifeless uniform void at nearly absolute zero temperature. Let me walk you through the timeline of endings, because this story is almost incomprehensibly long, so long that human minds cannot truly grasp the timescales involved. In about 100 billion years, the last stars will exhaust their nuclear fuel and fade to darkness. Think about that. Right now, the universe is full of stars. Brilliant blazing suns fusing hydrogen into helium, releasing tremendous energy that lights up space. In 100 billion years, all of them will be dead. No new stars will form because expansion will have stretched matter too thin for gravity to gather new stellar nurseries. The universe will enter what cosmologists call the degenerate era, dominated by cold stellar remnants, white dwarfs, the cooling cores of dead stars, neutron stars, the crushed remains of massive stars that exploded, black holes, gravity's ultimate victory. But even these objects won't last forever. After about 1034 years, even protons will decay into lighter particles. The atoms that make up your body, the atoms that form planets and stars, will spontaneously disintegrate. The strong nuclear force that holds protons together isn't actually permanent. Given enough time, quantum tunneling allows protons to fall apart. Matter as we know it will cease to exist. Only electrons, positrons, and photons will populate the expanding void, and even these particles will be spread so thin, separated by distances larger than the observable universe today, that they will never encounter each other. These timescales dwarf human comprehension. If the current age of the universe, 13.8 billion years, were compressed to a single second, the proton decay era would last longer than a billion years. Yet even this unimaginable stretch of time represents just a tiny fraction of the universe's future. After 100 years, black holes will become the only significant structures in the cosmos. Black holes evaporate through a process called Hawking radiation, slowly converting their mass into particles and energy. But this process takes an almost comically long time. A stellar mass black hole, formed from a star maybe 10 times the mass of the Sun, takes longer than the current age of the universe multiplied by 1050 to evaporate completely. Supermassive black holes, the giants lurking at galaxy centers with masses of billions of suns, will persist for 100 years. These monsters will be the last things to resist the tide of entropy. When the last black hole finally evaporates, releasing its last few particles into the void, the universe will achieve perfect heat death. No temperature differences will exist anywhere. No chemical reactions will be possible. No computation will occur. No life of any kind can survive. No complexity of any kind remains. The cosmos will have reached maximum entropy, a state of perfect equilibrium where nothing interesting can ever happen again. Every particle will be separated from every other particle by distances so vast that they might as well exist in separate universes. The observable horizon will have shrunk to encompass only a tiny region around each particle, and nothing will ever enter that horizon again. Perfect, eternal stillness. Heat death. This fate seems inevitable given our current understanding of physics. Dark energy accelerates expansion, spreading matter and energy across ever-increasing volumes of space. Unless dark energy somehow changes its behavior, and we have no evidence it will, expansion will continue forever, carrying the universe toward this cold, empty destiny. But expansion creates an even more immediate threat to the far future, one that astronomers living billions of years from now will face. As space stretches faster and faster, distant galaxies disappear from our observable universe. They don't get destroyed. They simply recede so rapidly that their light can never reach us again. From our perspective, they fade away and vanish beyond the cosmic horizon. In about 150 billion years, only our local group of galaxies will remain visible. Future astronomers living in the Milky Way, which by then will have merged with Andromeda and several smaller galaxies to form one giant elliptical galaxy, will observe a universe that appears to contain only one island of stars surrounded by infinite empty space. They will see no evidence of cosmic expansion because all the expanding regions will lie beyond their observational horizon. These future scientists might conclude they live in a small, static, eternal universe. A single galaxy floating alone in a void that has always existed and will always exist. The cosmic microwave background, our clearest evidence for the Big Bang, will also disappear. Expansion will redshift this ancient radiation to such long wavelengths that it becomes undetectable. Future civilizations will lose the very evidence that allowed us to understand cosmic origins. They will inhabit a universe that appears completely different from the one we observe today. They'll have access to the same scientific method, the same physical laws, but they'll see a cosmos stripped of its history. These future astronomers will be deceived by expansion itself, living in an age where the universe has erased the clues about its own nature. But even this gradual loss of cosmic perspective might be preferable to what some theories predict. If dark energy continues strengthening, if it's not a constant but rather a field that grows more powerful over time, expansion might accelerate so violently that it eventually overcomes every force holding matter together. Gravity would fail first, then electromagnetic forces, then even the strong nuclear force binding protons and neutrons in atomic nuclei. The universe wouldn't just expand forever, it would tear itself apart from the inside, destroying everything in a final catastrophe called the Big Rip. In about 22 billion years from now, dark energy might become so powerful that it tears apart every atom in the universe, shredding reality itself down to its fundamental components. This catastrophic end would make heat death look gentle by comparison. Instead of slowly fading away over trillions upon trillions of years, the universe would destroy itself in a final spasm of accelerating expansion that overwhelms every force in nature. Let me walk you through the destruction timeline because the Big Rip follows a terrifyingly methodical sequence. About 1 billion years before the end, dark energy becomes strong enough to overpower gravity on galactic scales. Galaxy clusters dissolve as space expands too rapidly for gravity to hold them together. Galaxies that have orbited each other for billions of years suddenly drift apart into the growing void, isolated from each other forever. The cosmic web, that beautiful large-scale structure where galaxies cluster along filaments surrounding vast voids, disintegrates. Every galaxy becomes an island, alone in an accelerating ocean of space. 200 million years before the end, expansion tears apart individual galaxies. The Milky Way, Andromeda, every galaxy throughout the universe dissolves. Stars get ripped away from their galactic homes and scattered across space as expansion overpowers the gravitational binding that held galaxies together for billions of years. Each star suddenly finds itself alone, no longer part of a galactic community, racing away from its neighbours as space stretches faster than gravity can pull them back together. 3 months before the Big Rip, expansion overcomes the gravitational binding of solar systems. Earth gets torn away from the Sun, the Moon spirals away from Earth. Every planet in every solar system throughout the universe suddenly finds itself alone in expanding space, lit only by the rapidly fading light of its parent star receding into darkness. Imagine looking up at the sky 3 months before the end and watching the Sun get smaller every day, not because it's dying, but because space itself is tearing your planet away from it. 30 minutes before the end, expansion becomes strong enough to overcome molecular bonds. The atmospheric gases surrounding every planet disperse into space, not because planets lose gravity, they still have mass, but because the space between gas molecules expands faster than molecular forces can maintain cohesion. Oceans boil away, not from heat, but because the space between water molecules expands faster than hydrogen bonds can hold them together. Every liquid becomes a gas, and every gas disperses into the growing void. Any life still existing at this point experiences its final minutes as the physical structures that support biology, cells, proteins, DNA molecules, begin stretching apart. 90 seconds before the Big Rip, expansion overwhelms electromagnetic forces. Molecules disintegrate, chemical bonds snap. Everything you'd recognize as matter, rocks, metals, organic compounds, breaks down into individual atoms as the electromagnetic force that holds atoms together into molecules finally succumbs to the stretching of space. 10 and just 19 seconds before the end, atomic nuclei disintegrate. The strong nuclear force, the most powerful force in nature, finally breaks. Protons and neutrons that have been bound together for billions of years suddenly fly apart as space between them expands faster than even nuclear forces can resist. Every atomic nucleus in the universe spontaneously disintegrates into individual protons and neutrons. The matter that formed stars, planets, and life reverts to its most fundamental components. At the moment of the Big Rip, space and time themselves might disintegrate. Some models suggest that space can only stretch so far before the very concept of distance breaks down. The metric that defines how to measure lengths and time intervals becomes infinite. Physics loses all meaning. Causality fails. Cause and effect stop working because the notion of nearby stops making sense. The universe doesn't just end, it becomes physically meaningless. But here's the critical point. This nightmare scenario only happens if dark energy behaves in a very specific way. If dark energy remains constant, if it's truly Einstein's cosmological constant, unchanging forever, the Big Rip will never occur. The universe will expand forever, approaching heat death gradually, but never experiencing this violent destruction. Only if dark energy strengthens over time does the Big Rip become inevitable. Only if whatever causes dark energy grows more powerful as the universe ages do we face this catastrophic end. Current observations suggest dark energy has remained roughly constant throughout cosmic history. The data points toward Einstein's cosmological constant, toward a gentler, though still ultimately fatal, heat death rather than a violent Big Rip. But the data isn't precise enough to completely rule out slow changes in dark energy. Future measurements of distant supernova, gravitational waves from colliding black holes, and other cosmic distance indicators will determine whether dark energy is strengthening. If it is, we can calculate exactly when the Big Rip will occur. Conservative estimates place it about 22 billion years in the future. More aggressive models suggest it could happen sooner, possibly within a few billion years, though this seems unlikely given current observations. Either timeline provides little comfort for long-term cosmic planning, yet even this ultimate destruction might not represent the end of everything. Some theories suggest that the Big Rip could trigger new episodes of cosmic inflation, creating fresh universes from the wreckage of the old one. The tearing apart of space-time might release energy that nucleates new bubble universes. The end becomes a beginning, death becomes birth. But before we can understand these cosmic endings, whether gentle heat death or violent Big Rip, we must examine more carefully how scientists actually measure the expansion that drives toward these fates. The story of cosmic expansion began with observations, not theories. How do you measure something as vast as the stretching of space itself? Astronomers measure the expansion of the universe by turning exploding stars into cosmic yardsticks, using the brightness of stellar death to map the growth of space itself. The challenge seems impossible at first. How do you measure distances to objects billions of light years away? How do you determine whether those objects are moving away from you? How do you distinguish between motion through space and the expansion of space itself? The answer lies in exploiting the predictable behavior of dying stars. Type Ia supernovae occur when white dwarf stars, the cooling remnants of stars like our Sun, accumulate too much matter from companion stars in binary systems. When the white dwarf crosses a critical threshold of about 1.4 solar masses, it explodes catastrophically. These stellar explosions release almost exactly the same amount of energy regardless of where they occur in the universe, making them perfect standard candles for distance measurement. It's like having lighthouses of known wattage scattered throughout the cosmos. Measure how bright they appear, compare to how bright they should be, and you can calculate exactly how far away they are. Here's how the measurement works. When a type Ia supernova explodes in a galaxy, astronomers measure its apparent brightness, how bright it looks from Earth. They compare this to the known intrinsic brightness of such explosions, which physics tells us should be roughly the same every time. Basic physics, objects appear dimmer when they're farther away, following the inverse square law. If something is twice as far away, it appears 4 times dimmer, 3 times as far, 9 times dimmer. By measuring the apparent brightness and knowing the intrinsic brightness, astronomers calculate the distance with remarkable precision. Simultaneously, they measure the redshift of the host galaxy by analysing the wavelengths of light from the explosion. Higher redshift means the light travelled through more expansion, indicating both greater distance and earlier cosmic time. By plotting distance versus redshift for hundreds of supernovae across billions of light years, astronomers map the expansion history of the universe. If expansion were constant, the relationship would form a straight line. If expansion were slowing due to gravity pulling galaxies together, distant supernovae would appear closer than expected. The universe would have expanded less during the light's journey. If expansion were accelerating, distant supernovae would appear farther away than expected. Space expanded more than anticipated during the light's journey to Earth. The data clearly shows acceleration. Supernovae that exploded when the universe was younger appear fainter than they should if expansion were constant. This means they're farther away than expected, proving that space expanded more than models predicted. Dark energy has been accelerating expansion for billions of years, and the evidence is written in stellar explosions scattered across cosmic time. But measuring cosmic expansion requires more than just supernovae. Astronomers use multiple techniques to build what they call the cosmic distance ladder, with each rung calibrated using the previous one. The bottom rung uses parallax measurements to nearby stars. As Earth orbits the Sun over the course of a year, nearby stars appear to shift position against the background of more distant stars. This parallax angle, combined with Earth's orbital diameter, provides precise distances to stars within a few hundred light years. It's like holding your thumb at arm's length and closing one eye, then the other. Your thumb appears to shift position against the background. The amount it shifts tells you how far away your thumb is. Astronomers do the same thing with stars, using Earth's orbit as the baseline. These parallax distances calibrate the next rung, Cepheid variable stars. Cepheids are supergiant stars that pulsate regularly, dimming and brightening with periods ranging from days to months. The longer the period, the more intrinsically luminous the star. By measuring a Cepheid's pulsation period, astronomers know exactly how bright it should be. Comparing this to its observed brightness gives its distance. Cepheids can be seen in galaxies up to 100 million light-years away, extending our distance measurements far beyond what parallax can reach. Cepheid distances calibrate the supernova measurements, which extend to billions of light-years. Each rung depends on the accuracy of the previous rungs, making the entire cosmic distance scale vulnerable to systematic errors. If parallax measurements are slightly off, Cepheid distances will be wrong, and supernova distances will be even more wrong. This vulnerability has created one of the biggest controversies in modern cosmology. Different measurement techniques give slightly different values for the Hubble constant, the number describing how fast the universe expands. Local measurements using the distance ladder suggest space expands at about 73 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.26 million light-years, galaxies are receding 73 kilometers per second faster. A galaxy 1 megaparsec away recedes at 73 km/s. A galaxy 2 megaparsecs away recedes at 146 km/s, and so on. But measurements from the cosmic microwave background suggest a lower value of about 67 km per second per megaparsec. This technique uses the ancient light from the early universe, analysing its patterns to determine cosmic properties including the expansion rate. This 6% discrepancy might not sound significant, but it represents a genuine crisis in cosmology. Both measurement techniques are sophisticated and precise. Both have been checked and rechecked for errors. Either one of the techniques contains unknown systematic errors that have evaded detection despite decades of careful work, or our understanding of cosmic evolution is fundamentally flawed. Perhaps dark energy behaves differently than we think. Perhaps there's new physics we haven't discovered yet. The resolution might require revolutionary new physics, or it might simply require discovering subtle systematic errors in one of the measurement techniques. Yet despite this controversy, both techniques agree on the most important conclusion. The universe is expanding, and that expansion is accelerating. The disagreement is over the precise rate, not the fundamental fact. But how do scientists translate these observational measurements into mathematical descriptions of cosmic evolution? How do you capture the entire expansion history in a form that allows predictions about the cosmic future? The entire expansion history of the universe can be captured in a single mathematical function that describes how space grows over time, and this function reveals the cosmic future. Scientists call this the scale factor, usually represented by the letter AT, a function of time. This simple variable encodes everything about how distances change as the universe evolves. When the scale factor doubles, all distances double. When it triples, all distances triple. The scale factor makes cosmic expansion mathematically precise and predictable. By convention, cosmologists set the scale factor to 1 at the present time. This means that earlier in cosmic history, when the universe was smaller, the scale factor was less than 1. In the future, when the universe will be larger, the scale factor will exceed 1. Here's what makes this framework so powerful. The scale factor connects observable quantities to cosmic time. When you observe a galaxy with redshift z, you're seeing it at a time when the scale factor equaled 1. A galaxy with redshift 1 existed when the scale factor was 0.5, meaning the universe was half its current size. A galaxy with redshift 2 existed when the scale factor was 0.33, when the universe was 1/3 its current size. This allows astronomers to reconstruct cosmic history from redshift measurements. Light from the cosmic microwave background has a redshift of about 1090. This radiation comes from when the scale factor was roughly 0.001, meaning the universe was 1,000th its current size in each dimension. The volume of space was 1 billion times smaller when that light was emitted. Everything in our observable universe was compressed into a region smaller than the current solar system. But the scale factor does more than describe the past. Combined with Einstein's field equations from general relativity, it predicts the future evolution of cosmic expansion based on the current contents of the universe. The acceleration of expansion depends on how the scale factor changes with time. If the scale factor grows linearly with time, expansion proceeds at constant rate. If it grows faster than linearly, expansion accelerates. If it grows slower than linearly, expansion decelerates. Current observations show that the scale factor has been growing faster than linearly for about 5 billion years, confirming cosmic acceleration driven by dark energy. The mathematics reveals 3 possible futures depending on dark energy's properties. Scenario 1. Dark energy remains constant. The scale factor will grow exponentially forever. Space will expand at an accelerating rate, but the acceleration itself will approach a constant value. This leads to heat death, as matter spreads ever thinner across growing space. Scenario 2. Dark energy strengthens over time. The scale factor will grow faster than exponentially, leading to the Big Rip scenario where expansion eventually overcomes all forces, tearing apart every structure in the universe. Scenario 3. Dark energy weakens or becomes negative. The scale factor might eventually stop growing and begin shrinking, leading to a big crunch where the universe collapses back on itself, ending in a hot, dense state similar to how it began. Current data suggests the first scenario is most likely: constant dark energy, eternal expansion, eventual heat death. But the scale factor framework reveals something even more profound about the nature of cosmic expansion. The expansion rate at any given time depends only on the total energy density of the universe at that time. More energy density means faster expansion. In the early universe, when matter and radiation were compressed into a small volume, the energy density was enormous. This drove very rapid expansion that gradually slowed as the universe grew and energy density decreased. About 5 billion years ago, dark energy became dominant and expansion began accelerating again. The scale factor mathematically encodes this entire transition from deceleration to acceleration. By fitting theoretical curves to observational data, cosmologists can determine the relative amounts of matter, radiation, and dark energy at different epochs. These calculations reveal that our universe is currently about 68% dark energy, 27% dark matter, 5% ordinary matter, everything we can see and touch. The scale factor approach also predicts how these percentages will change over time. As space expands, matter becomes more dilute, but dark energy maintains constant density. This means dark energy's influence will grow stronger in the future. Eventually, dark energy will dominate so completely that expansion approaches pure exponential growth, with the scale factor doubling at regular intervals forever. But this entire mathematical framework for understanding expansion, this elegant system for describing how space grows, rests on insights that emerge from one of the greatest scientific mistakes in history. What happens when a genius makes an error that accidentally predicts the future? Albert Einstein added a term to his equations of general relativity that he later called his greatest blunder. But that term turned out to be essential for understanding the accelerating expansion we observe today. In 1917, Einstein faced a significant problem with his newly completed theory of general relativity. The equations predicted that the universe should either be expanding or contracting. They allowed no static, unchanging cosmos, but everyone knew the universe was static and eternal. That's what astronomers believed at the time, based on observations that seemed to show stars and nebulae in fixed positions. The idea of a dynamic, evolving universe seemed absurd, almost offensive to scientific sensibilities. How could the entire cosmos be changing? Where would it expand to? What would drive such expansion? The question seemed nonsensical. Einstein trusted the observational evidence and modified his equations. He added what he called the cosmological constant, represented by the Greek letter lambda, L. This term acted like a repulsive force that could exactly balance gravity's attractive pull, allowing the universe to remain static despite containing matter. The cosmological constant represented the energy of empty space itself. Einstein envisioned this space energy as a fundamental property of the vacuum, creating a gentle outward push that prevented gravitational collapse. Just enough repulsion to balance attraction, just enough to keep the universe perfectly balanced and unchanging. For more than a decade, this seemed like a reasonable solution. The equations worked. The universe appeared static. Einstein was satisfied. Then in 1929, Edwin Hubble dropped a bomb on this comfortable picture. Hubble discovered that distant galaxies are racing away from us. The universe wasn't static after all. It was expanding just as Einstein's original equations, without the cosmological constant, had predicted. The observational evidence that convinced Einstein to add the cosmological constant was simply wrong. Astronomers had misunderstood what they were seeing. The universe was never static. Einstein quickly abandoned the cosmological constant, reportedly calling it his greatest blunder. If he had trusted his original equations instead of the flawed observations, he would have predicted cosmic expansion decades before Hubble discovered it. Einstein could have been remembered as the scientist who predicted the expanding universe purely from theoretical reasoning, one of the most remarkable predictions in the history of science. Instead, he second-guessed himself and added an unnecessary term to his equations, or so it seemed for decades. But the story doesn't end there. In 1998, everything changed again. Astronomers discovered that cosmic expansion is accelerating. Something is pushing space apart with increasing strength, exactly what Einstein's cosmological constant was designed to do. Einstein's blunder turned out to be essential for understanding the universe. The accelerating expansion requires some form of dark energy that behaves exactly like Einstein's cosmological constant, a uniform energy density that fills all of space and creates repulsive gravitational effects. Current observations suggest the cosmological constant provides the best fit to the data. If this interpretation is correct, then Einstein's intuition about the energy of empty space was remarkably prescient, even though he added it to his equations for entirely the wrong reasons. He realized that vacuum itself might possess energy and gravitational effects. He just didn't realize that this vacuum energy would drive acceleration, rather than maintain a static universe. The value of the cosmological constant in our universe is tiny but non-zero. Each cubic centimeter of empty space contains about 10 to the power 10 joules of dark energy. This seems insignificant. It's millions of times less energy than the rest, mass energy of a single electron. But when multiplied by the vast volume of the observable universe, it totals more energy than all the matter and radiation combined. Einstein's supposedly unnecessary term dominates cosmic evolution. But the cosmological constant creates a new problem that Einstein never anticipated, one that represents perhaps the deepest mystery in theoretical physics. If vacuum energy drives acceleration, why is the value so absurdly small? Quantum field theory, our best theory of how particles and fields behave, predicts that vacuum energy should be about 10^120 times larger than observed. Let me emphasize how wrong this is. Physics predicts a value that's off by 120 orders of magnitude. That's not a small error. That's not even a large error. That's such a catastrophically huge error that it suggests something is fundamentally wrong with our understanding. This vacuum catastrophe represents one of the deepest mysteries in physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism suppresses 99.999%, with 120 decimal places of nines, of the vacuum energy while allowing just enough to remain active to drive observed acceleration. Resolving this mystery might require entirely new physics beyond anything Einstein or anyone else has imagined. Alternative theories propose that dark energy isn't a cosmological constant at all, but rather a dynamic field that changes over time, potentially avoiding the vacuum catastrophe while still explaining accelerated expansion. But current observations favour Einstein's original insight about the energy of empty space. The irony is profound and almost poetic. Einstein added the cosmological constant to prevent expansion, then removed it when expansion was discovered. Modern cosmology has restored it to explain why expansion is accelerating. His greatest blunder became his most prescient insight. Yet even Einstein's genius built upon observations that revolutionized our understanding of the cosmos. Before Einstein could develop general relativity, before anyone could discuss cosmic expansion, someone had to first discover that the universe extends far beyond our galaxy. What happens when an astronomer points a telescope at the sky and discovers that everything humanity thought it knew about the universe is completely wrong? Edwin Hubble spent night after night in 1929 measuring the distances and velocities of distant galaxies and accidentally discovered that the entire universe is flying apart. Working at Mount Wilson Observatory in California with the world's largest telescope, the 100-inch Hooker telescope, Hubble was initially trying to settle a debate about the nature of spiral nebulae. Were these cloudy, spiral-shaped objects part of our Milky Way galaxy, or were they separate island universes at vast distances beyond our galaxy? Using Cepheid variable stars as distance indicators, Hubble calculated that these spiral nebulae lay millions of light-years away, far beyond the boundaries of the Milky Way. They were indeed separate galaxies. This discovery alone expanded the known universe by an almost incomprehensible factor. Humanity suddenly realized we live in one galaxy among countless galaxies, rather than in the only galaxy that exists. But that wasn't the revolutionary discovery that changed everything. As Hubble plotted galaxy distances against their velocities, measured from redshifts in their spectra, he noticed an impossible pattern. Every galaxy was moving away from us. Not just a few galaxies, not just distant galaxies. Every single galaxy he could measure showed redshifted light indicating motion away from the Milky Way. This seemed to place Earth at the center of a cosmic explosion, as if we occupied a special position from which everything was fleeing. It violated the Copernican principle that Earth holds no privileged position in the cosmos. Even more disturbing, the farther away a galaxy was, the faster it appeared to be receding. Galaxies twice as distant moved away twice as quickly. Galaxies 3 times farther moved 3 times faster. This relationship, now called Hubble's law, suggested a direct proportionality between distance and recession velocity. At first, Hubble interpreted this pattern as evidence for motion through space. He imagined galaxies racing away from us through a static cosmic arena, like shrapnel from an explosion expanding into empty space. But this interpretation created impossible problems. Why should we be at the center of everything? Why would all galaxies be moving away from us specifically? The resolution came from understanding that space itself was expanding. A concept that seems simple now, but was revolutionary at the time. Imagine dots painted on a deflating balloon, but run the process in reverse. As the balloon inflates, every dot sees every other dot moving away. The farther apart 2 dots are, the faster they separate. Yet no dot is special. No dot sits at the center of expansion. Each dot experiences the same pattern Hubble observed. This insight transformed Hubble's discovery from a measurement of galactic motion to evidence for cosmic expansion. Galaxies aren't moving through space like cars on a highway. Space itself is stretching, carrying galaxies along like raisins in rising bread dough. Hubble's law became the first observational evidence for the expanding universe, and it completely revolutionized cosmology. The proportionality constant in Hubble's law, now called the Hubble constant, describes how fast space expands. A larger Hubble constant means faster expansion. A smaller constant means slower expansion. Hubble's original measurements gave a constant about 7 times larger than modern values, suggesting a universe only 2 billion years old. This created serious problems because geological evidence indicated Earth was older than 2 billion years. How could Earth be older than the universe itself? The error lay in Hubble's distance measurements. He confused two different types of variable stars, leading to systematic underestimation of galactic distances. When astronomers corrected these errors, the age of the universe increased to comfortable values well above Earth's age. But Hubble's discovery of the distance-velocity relationship remained valid. Modern measurements confirm that expansion follows Hubble's law to remarkable precision across cosmic distances. From nearby galaxies a few million light-years away to the most distant observable galaxies, billions of light-years distant, the relationship holds. This consistency proves that expansion is a global property of space itself, not just local motions of individual galaxies. Hubble's work established the first cosmic distance scale, allowing astronomers to map the three-dimensional structure of the universe. Before Hubble, astronomy was essentially two-dimensional, limited to measuring positions on the celestial sphere. After Hubble, cosmology became possible. His discovery transformed our understanding of humanity's place in the cosmos. We don't live in a static, eternal universe. We inhabit a dynamic, evolving cosmos that began in a hot, dense state and has been expanding and cooling ever since. The expanding universe revealed by Hubble's observations became the foundation for Big Bang cosmology, the standard model of how the universe began and evolved. But Hubble's law also raised a fundamental question about cosmic destiny. Would expansion continue forever, or would gravity eventually halt it and cause the universe to collapse back on itself? The answer depends on how much matter the universe contains, which led to one of cosmology's deepest mysteries, and one of its most surprising discoveries. There exists a precise amount of matter that determines whether the universe expands forever or eventually collapses back on itself, and we live remarkably close to this cosmic knife's edge. This critical density equals about 5 hydrogen atoms per cubic meter of space. Think about that. 5 atoms per cubic meter. That's almost perfectly empty by any reasonable standard. Better vacuum than the best laboratory can create. Yet this tiny amount of matter, scattered across vast volumes of space, determines the ultimate fate of everything. The physics behind critical density comes from the competition between expansion and gravity. Expansion carries galaxies apart, spreading matter across ever-increasing volumes of space. Gravity pulls matter together, trying to reverse the expansion and cause cosmic collapse. The strength of gravity depends on how much matter exists per unit volume, the density. If the universe contains more than critical density, gravity wins. Expansion slows, stops, and reverses into a big crunch. All matter eventually collapses back into a hot, dense state, possibly ending in a singularity similar to the Big Bang but in reverse. If the universe contains less than critical density, expansion wins. The cosmos expands forever, approaching heat death as matter spreads infinitely thin and temperatures drop toward absolute zero. If the universe contains exactly critical density, perfect balance, expansion asymptotically approaches zero velocity but never quite stops. Like throwing a ball upward with exactly the right speed to reach infinite height while slowing to zero velocity. For decades, measuring the actual density of the universe became cosmology's holy grail. The challenge seemed straightforward. Count all the matter, divide by the volume it occupies, and compare to critical density. But reality proved far more complex. Most of the matter in the universe appears to be invisible. Observations of galaxy rotation curves, how fast stars orbit around galactic centers, revealed that galaxies contain much more mass than their visible stars suggest. Stars in the outskirts of galaxies orbit faster than they should based on visible matter alone. Either Newton's laws of gravity stop working at large scales, possible but unlikely, or galaxies contain huge amounts of invisible matter creating additional gravitational pull. This invisible mass became known as dark matter. It doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. It interacts only through gravity, making it detectable only through its gravitational effects on visible matter. Think of dark matter like a ghost that doesn't interact with light, but has mass and gravity. You can't see it directly, but you can see its influence on things around it. Despite being invisible, dark matter outweighs ordinary matter by more than 5 to 1. For every gram of normal matter, atoms, molecules, all the stuff you can see and touch, there are more than 5 grams of dark matter holding galaxies together through gravity. When cosmologists included dark matter in their density calculations, they found a universe with about 30% of critical density. This suggested a universe that would expand forever, gradually approaching heat death. Then came the discovery of dark energy in 1998, and everything changed again. Dark energy doesn't just add to the total energy density of the universe, it fundamentally changes expansion dynamics by creating repulsive gravity instead of attractive gravity. In Einstein's equations, energy density with negative pressure can drive accelerated expansion. Dark energy behaves exactly like this, and it makes up roughly 68% of everything in the universe. Current observations suggest we live in a universe with 68% dark energy, 27% dark matter, 5% ordinary matter, everything we can see. This combination puts us remarkably close to critical density when properly accounting for dark energy's negative pressure effects. The universe appears to be balanced almost exactly on the edge between different possible geometries. This near critical density creates what cosmologists call the flatness problem. Why should the universe be so close to critical density? In most models of cosmic evolution, the density either quickly becomes much larger than critical, leading to rapid collapse, or much smaller than critical, leading to empty expansion. Maintaining near critical density requires incredibly precise fine-tuning of initial conditions. The early universe needed to have a density that matched critical density to better than 1 part in 10^60 for the universe to still be near critical density today. That's like balancing a pencil on its point and having it remain standing for billions of years. Tiny deviations would quickly amplify, causing the universe to either collapse or thin out dramatically. Cosmic inflation provides a possible solution to the flatness problem. During inflation's exponential expansion, any initial curvature gets stretched so flat that the universe emerges from inflation very close to critical density. It's like inflating a balloon to the size of the observable universe. Any curvature becomes undetectable at small scales. The surface looks perfectly flat from your perspective. This might explain why we observe near critical density today. Inflation set the initial conditions, and the universe has remained close to critical ever since. But the coincidence remains troubling from another perspective. We happen to live at the cosmic epoch when dark matter, dark energy, and ordinary matter have comparable influence on cosmic evolution. A few billion years ago, matter dominated. Dark energy existed but was negligible compared to matter's gravitational influence. A few billion years in the future, dark energy will dominate completely. Matter's influence will be negligible compared to dark energy's accelerating push. We exist during the brief transition period when all 3 components matter roughly equally. Why now? Why should observers arise during this special epoch? This might be selection bias. Perhaps observers can only exist during epochs when matter density is comparable to critical density. Earlier times might be too violent for complex structures to form. Later times might be too empty for new stars and planets to develop. We observe near critical density not because the universe was fine-tuned for us, but because only near critical universes at specific epochs can produce observers to notice the coincidence. Yet even this reasoning assumes we're alone in the cosmos, the only universe expanding from its own Big Bang. What if we're not alone? What if expansion is happening in countless other realities alongside our own, each with different densities, different expansion rates, different fates? Right now, while you read these words, trillions of other universes might be undergoing their own expansion histories, each growing from its own Big Bang in directions you cannot perceive or imagine. These parallel universes wouldn't exist far away in our space. They would exist in entirely separate spaces that share no connection with ours. Each universe would have its own 3 dimensions of space, its own time dimension, its own expansion history, its own physical laws. The multiverse could be expanding on multiple levels simultaneously, with each level operating according to different rules and timescales. In eternal inflation models, our observable universe represents just one tiny patch of a much larger inflated region. But inflation doesn't stop everywhere simultaneously. Quantum fluctuations continuously trigger new episodes of inflation throughout the larger space, creating bubble universes that expand and evolve independently. Each bubble develops its own physics, its own constants of nature, its own expansion dynamics. While our universe has been expanding for 13.8 billion years, other bubbles might have been expanding for trillions of years. Still others might have just begun their expansion a few million years ago. Some bubble universes might expand much faster than ours due to stronger dark energy. Others might expand more slowly due to higher matter densities. A few unlucky bubbles might have already collapsed back on themselves in big crunches, their entire histories playing out in cosmic eye blinks, creating and destroying galaxies and stars and possibly even civilizations in brief flashes of existence. Other bubbles might be approaching big rip scenarios where expansion tears apart their fundamental structures, destroying everything in violent catastrophes we'll never witness. Each bubble universe experiences expansion differently. Some expand into heat death, some collapse into big crunches, some rip themselves apart. Every possible expansion history plays out somewhere in the multiverse. But the multiverse concept extends even further than eternal inflation. Some interpretations of quantum mechanics suggest that every quantum measurement creates parallel realities where different outcomes occur. In this many worlds interpretation, the universe constantly splits into multiple versions. Each version continues expanding according to its own quantum history. The number of parallel expanding universes would be literally infinite, with new ones branching off every moment at every quantum event throughout space. Most would be nearly identical to ours, differing only in microscopic quantum details, the spin of a single electron, the position of one photon. Others would diverge dramatically due to different sequences of quantum events accumulated over billions of years. In some parallel universes, dark energy might be stronger, leading to faster acceleration and earlier heat death. In others, dark energy might be weaker, allowing gravity to eventually halt expansion. Every possible expansion history plays out somewhere in the quantum multiverse. This creates a disturbing realization. Parallel versions of you are experiencing every possible cosmic fate. Some versions live in universes approaching heat death, where they'll witness the gradual dimming of all stars and the final evaporation of all black holes. Others inhabit cosmos heading toward big rips, where they'll experience the violent destruction of everything as space tears itself apart. Still others exist in universes that will eventually collapse into big crunches, where they'll see distant galaxies begin approaching rather than receding, where the cosmic microwave background will start blue shifting rather than red shifting, where temperatures will rise as the universe compresses. The expansion of space affects every possible version of reality in every possible way. But this raises profound questions about meaning and significance. If infinite universes are expanding in infinite ways, does our particular expansion history matter? Does anything we do or experience have significance when infinite other versions exist experiencing different outcomes? Some argue that the multiverse makes our universe's fate irrelevant. Even if our cosmos approaches heat death or gets torn apart in a big rip, infinite other versions of you continue existing in universes with different expansion patterns. Others contend that each universe remains meaningful to its inhabitants, regardless of how many parallel versions exist. Your experiences matter to you, even if other yous exist elsewhere. The debate touches on fundamental questions about identity, consciousness, and the nature of meaning itself, questions that might not have definitive answers. But one thing remains certain. In our universe, in this branch of the multiverse, or this bubble of eternal inflation, expansion continues relentlessly toward one of the possible endings we've discussed. And as expansion carries us toward that ending, whether heat death or big rip or something else entirely, it raises one final question that brings us back to where we started. What does it all mean? Why does the universe expand at all? And what can we learn from the fact that asking, what does it expand into, is the wrong question entirely? The question, what is the universe expanding into, is like asking what's north of the North Pole. Understanding why reveals the deepest truth about the nature of reality itself. When you ask what the universe expands into, you're making an assumption that seems perfectly reasonable but is actually impossible. You're assuming that expansion requires pre-existing space to expand into, like a balloon needing air or a city needing countryside. But the universe is not like a balloon. The universe is space itself. When space expands, it doesn't grow into something else. It creates the very concept of something else as it grows. There is no external arena because the universe defines what external means. This isn't a limitation of human language or a failure of scientific imagination. It's a fundamental feature of reality. Before expansion, the concepts of into and outside don't exist. Expansion doesn't just create more space, it creates the logical framework that makes spatial relationships meaningful. The universe doesn't expand into anything because it creates the very notion of anything as it expands. Think of it this way. Asking what the universe expands into is like asking what caused the first cause or what contains the container of everything. The question assumes categories that only make sense after the thing you're asking about has already happened. The universe expands by becoming more universe, not by growing into non-universe. This realization transforms our understanding of cosmic expansion from a mechanical process into something far more profound. Expansion isn't just the universe getting bigger, it's reality bootstrapping itself into existence, moment by moment, creating space and time and possibility from quantum foam and vacuum energy. Every cubic inch of new space that comes into being creates new possibilities for matter, energy, structure, complexity, and meaning. The universe doesn't expand towards some predetermined goal. It expands into the infinite potential for what can be. Think about what this means for your existence. You're not a passenger on a cosmic vehicle traveling towards some destination. You are part of the process by which reality creates itself. Your consciousness, your questions, your desperate need to understand what the universe expands into. These are all expressions of the universe coming to know itself. The expansion we observe isn't separate from us. We are expansion. We are space and time and matter and energy organizing themselves into patterns complex enough to ask questions about their own existence, to wonder where expansion leads, to struggle with concepts that our brains evolved to understand motion through space, but not the creation of space itself. Every thought you have exists as electromagnetic patterns in neural tissue that exist as molecular structures, that exist as atomic bonds, that exist as quantum fields vibrating in expanding space. You're made of expansion. You're a temporary complexity that arose because expansion created enough room and time for stars to form, for heavy elements to be forged in stellar furnaces, for planets to coalesce, for chemistry to become biology, for biology to become consciousness. None of this would be possible in a static universe. Without expansion, the universe would either collapse immediately under its own gravity or remain forever frozen in simplicity. Expansion creates the dynamic backdrop that allows cosmic drama to unfold, stars igniting, planets forming, life evolving, consciousness emerging, observers arising to wonder about it all. This perspective resolves the paradox of cosmic expansion while revealing an even deeper mystery. If the universe creates its own space and time, if it serves as its own stage and its own audience, then what we call existence might be far stranger than any science fiction has imagined. We might be living inside a self-creating, self-sustaining process that has no beginning or end in any conventional sense, no inside or outside, no purpose beyond the magnificent fact of its own becoming. The universe expands into itself, creating infinite room for infinite possibilities, including the possibility of beings like us who can stand in awe of the whole impossible, beautiful process. Let me leave you with this final thought. You spent the last 3 hours learning about cosmic expansion, about inflation and dark energy, about parallel universes and extra dimensions, about heat death and big rips and the ultimate fate of everything. But the most profound truth was always hiding in plain sight. The question itself, what does the universe expand into, led us on this journey not because it has an answer, but because struggling with it reveals what expansion really is. The universe expands into mystery, into wonder, into the endless capacity for more questions, more discoveries, more moments of recognition that we are part of something vastly larger than ourselves, yet intimately connected to our smallest thoughts. We are the universe asking what it expands into. We are the expansion asking where it's going. We are space and time awakening to their own existence and marveling at the infinite creativity of the process that brought us into being. 3 hours ago, you probably thought expansion meant something moving into empty space, growing into a container, filling a pre-existing void. Now you understand that expansion is reality creating itself, space manufacturing more space, existence bootstrapping itself into being through quantum fluctuations and vacuum energy, and the strange mathematics of general relativity. This understanding doesn't diminish the mystery, it deepens it. We've replaced a simple question with a profound realization that existence itself is stranger and more beautiful than we ever imagined. The universe doesn't expand into anything because it is everything. All of space, all of time, all of possibility. And you, yes, you specifically, are a small part of that everything. A brief complexity that arose during a brief epoch when expansion created conditions suitable for consciousness. A temporary pattern that gets to experience the impossible fact that anything exists at all. In that recognition, the question transforms from a puzzle to be solved into a celebration of the magnificent impossibility of existence itself. The universe expands. We exist within that expansion, and for a brief cosmic moment, we get to wonder why, to search for answers, to marvel at the beauty of reality creating itself from nothing and expanding into infinite possibility. That's not just physics. That's poetry written in the language of mathematics, performed on a stage made of space-time, observed by consciousness that emerged from quantum foam. The universe expands into mystery and wonder, and the infinite capacity for meaning. And now you understand why asking where it's expanding to was the perfect question all along. Not because it has an answer, but because the journey to understand why it can't have an answer reveals the deepest truths about existence itself. Thank you for joining me on this journey through deep time across cosmic scales into the heart of the greatest mystery in science. The universe is expanding, we are expanding with it, and the story continues moment by moment as reality creates itself from nothing and expands into everything